Hello everyone. In the previous video, we have discussed about various heap properties like what is the maximum number of nodes, what is the maximum number of leaves, and the leaves will be from where to where, all these type of properties. Now in this video, we will cover the basic heap operations. Fine. We have basically 5 basic heap operations. First one is heapify, second one is delete max, third one is increase key, and fourth one is insert operation. Finally, find maximum. Means we will study 5 basic operations on heap. After that, we will go to heap building, heap and heap sort. So in this video, we will cover these first 2 operations on heap, that is heapify and delete max. Now let's see first operation, that is heapify operation. First, we will see 1 or 2 examples. After that, we will go to this algorithm. So, and after that, we will see by the recurrence equation what is the time complexity of this and what is the space complexity of this. And instead of recurrence equation, we will also see how we can simply calculate its time complexity and space complexity in simple and easy terms, so that in exam we don't have to be panic and we don't have any need to make an recurrence equation and then solve the equation to find out the time complexity and space complexity simply. So first we take an example, and firstly go to my previous 2 videos on heap sort, where I have already mentioned about all the basic concept of heap. What is max heap, what is minimum heap, what is the different properties of heap, all these things. And for now in a heap, leaf node will be from n by 2 plus 1 to n. Simply, and non-leaf node will be till n by 2. Means simply we can check leaf node is n by 2, floor plus 1 to n. Here, what is total number of nodes? 10 elements are there. Means leaf node will be from where to where? 10 by 2 plus 1 to 10. This is simply 6 to 10. We can simply check leaf node starts from 6, 7, 8, 9, 10 till 10. And if we talk about non-leaf node, simply from the first element to n by 2. That is 5. First element to fifth element. These are non-leaf. So simply there is a property of heap once and leaf node starts. Means once we see a leaf node in a heap, then after that index position, all nodes will be leaf node only. Simply, you can take any example and build a heap top to down, level by level. Like first we insert first element, then left, then right. When this level is complete, then we will move to next level. When this is complete, then we will insert here in the same way, right? So simply, the main property which you have to remember for this time, the leaf node will start from n by 2 plus 1 to n. Means when one leaf starts in a heap, after that leaf node, you will get all leaf nodes only. Okay, simple. There is at 6 location, there is a leaf node, 7 leaf, 8 leaf, 9 leaf, 10th leaf, 7. Now we will show how this heapify operations work. It is very simple. Simply, we will start from the very first element, that is root. See, by default, I have already told about mean heap and max heap, and by default we take maximum heap. And all the properties and all these operations we will take as max heap only. Okay. So max heap, I have already told what is the property of max heap. That is, parent should be greater or equal to its children. Simply, we have to check this one only. We will start from root, from index position 1, then 2, then 3rd, then 4th, and so on. Simple, one by one. We will start from first element and we will compare this element with its children. 14 and 10. Which one is greater? 14 is greater. And the parent is smaller than its children. Simply, in these two, greater is 14, we will swap. 14 will go there and 1 will go move here. Simply. We will do one more example. This will be very easy. Okay. Simple. First position is okay. Now we will go to second index position and we have to compare just parent and its children. We don't have to worry about rest of these. Simple. Now we will go to index position second. This is 1 and its children is 8 and 7. And which one is greater? 8. And parent is smaller than its children. Simply, what we have to do in MaxHeap, the parent should be greater than its children. Simply, 8 is greater. 8 will go there. And 1 will go here. Simple. Second position is okay. Parent is greater than its children. Now we'll move to the next position. This is 10, 9, 3. Parent is greater than its children already. This condition is satisfied already. 10 is greater than its children, 9 and 3. So we don't have any need to swap and all this. Simple. Now we will move to the next index position, that is 4. Now here parent is 1, children is 2 and 4. Simply parent is smaller than its children. But what MaxHeap says, the parent should be greater or equal to children. Now which one is greater than that? 4 is greater. So 4 will go there and 1 will come here. Simply now you can see parent is greater than its children. This is okay. Now we will move to next index position. Here is 7 and here is 6. This is simple. Parent is already greater than its child. Simple. Then it is okay. So simply what we have to do in heapify operation, we have to simply start from root element, means first index position, and just have to see to clear the max heap property or min heap property. If max heap property is satisfied, then you have to do nothing. You will just move to the next element. But if max heap property does not satisfy for this element, then what we will do? We will compare these children and the maximum children will go there and this position will go there. Simple. We will take one more example. Now we will see the second example. Simple. In the same way, first we indicate the index positions. There are total 8 elements and the leaf nodes will be from n by 2 plus 1 to n. Means 8 by 2 plus 1 to n means 8. 5 to 8. This is to solve, but manually we can see from 5 to 8. 5, 6, 7, 8. These are leaf nodes. And once a leaf node starts in a heap, all the nodes after this leaf position, all will be leaves only. Simple. So in the same way, first we will start from the very first element, that is root. And we are doing max heapify operation simply. 15 is already greater than its children. This is okay. We don't have any need to swap and all this. Now we will come to the next index position, that is 2. Here parent is 0 and children is 8 and 7. Property is not satisfying for max heap. Parent should be greater than children, but here parent is smaller than children. What we will simply do? Which one is greater between 8 and 7? 8 is greater. Simply 8 will go there and 0 will come here. Simple. Second is okay. You can see parent is greater than its children. Now we will go to next index position. This one is 5. Parent is 5 and children is 3 and 2. This is already satisfying the property of max heap, that is parent should be greater than its children. 5 is already greater than its children. So this is okay. We don't have any need to swap and all this. Okay. We will now, this is third index position. We will move to fourth index position. This is fourth index position. Parent is 0 and child is 1. Means this is not satisfying the max heap property. In max heap, parent should be greater than children. So we will simply, children will go there and parent will move there. Simple. Now we will move to next index position, fifth. But there is no children, nothing to compare, means it is by default max heap. Next children, this is by default max heap because there is no children, nothing to compare, means by default this is max heap. In the same way, this child and this child also. I have already discussed this property that every leaf node is by default a min heap or max heap. Because see, you can say simply, there is nothing to compare. These are by default min heap or max heap simply. So these are two examples. Now we will simply see how this algorithm is. We have discussed two examples here, and now we will see its recurrence equation. And here you can simply see what is this algorithm is running. This is working the same way. We are giving two comparisons. Firstly, we have an array of elements size suppose 10, and we are starting from first element, root element. We are going to left child and right child. Then we are comparing whether this is greater than this, and if this is greater than this is largest, left largest. If this is not greater, means this one is larger. Simply, firstly we are comparing these two, and if this is larger, means largest is this. Otherwise, if this is not largest, largest is this. Simply. Now in the second comparison, what we are comparing? Simply, R is less than heap size. See these two things. These are just to check whether we are talking about leaf node or non-leaf node. As I have already told, leaf node is by default max heap or min heap. So we don't have to check for leaf nodes. We will check, means we will further proceed only if these are internal nodes. Simply because we will check for the internal nodes only. Leaf nodes are already max heap or min heap. Simply these two conditions are for that. Next we are simply comparing A of largest. Which one is, suppose we have I, we are comparing all this, and in the same way. Simply, now finally we are exchanging the value. Simple. You take one or two example more. You can take any value, random value, and see how this is working. This is very simple. This is the same way as this is running. Now we will see what is the time complexity and what is the recurrence equation. Now see about space complexity and time complexity of Hippie operation. First we talk about space complexity. I have discussed in my previous video what is space complexity. Simply the number of levels in a recursion tree. And here we can clearly see heap is a almost complete binary tree, and the tree will grow equally in both the direction. Means the tree will grow in log form. Log form means tree is growing equally in both direction. And space complexity is simply the number of levels in a tree. And here we can clearly see the number of levels in a tree is log, and because the tree is growing in logarithmic form. So space complexity is order of log n. And if we talk about time complexity, this is very simple. See, if we are there, what we are doing? We are making two comparisons, one for this, one for this. And then same way for next one for this, one for this. Next one for this, one for this. Till how many times? Log n times. Because our tree is growing in log form. So for one comparison, for one position down, how much comparison we are doing? Two comparisons for this and this. So 2 into what is tree height? How many comparison we have to do? Log n times log n. Simply 2 is constant, we can ignore. You simply remember time complexity is order of log. So we have seen Hippie operation. This is simply what we do. We insert the element simply level by level in this way. Now we'll start from the very first element. We will compare. If we are talking about max heap, we will compare whether parent is greater than his children or not. If this is not, then we will swap with the greater children simply, and we will start from first position, then next simply, and start with a leaf node. Once we see a leaf node in the way, after that leaf node, all nodes will be leaves only. Simply here, what is the first leaf node? 9 is first leaf node. Then after this, 3 is also leaf, this is also leaf, this is also leaf, and this is also leaf. Simply. And if we talk about space complexity and time complexity, what is space complexity? Simply number of levels in a tree. And we know heap is a complete binary tree, so the levels or the tree will grow in the log form. So simply log n. And if we talk about time complexity, mainly how much comparison we are doing to move the next level. We are doing 2 comparison. And total number of levels, log n. Simply 2 will be ignored. You can remember simply log n. So you can remember one more thing. All heap operations take order of log n time. Time complexity will be same for all the heap operations. I am talking about heap operation, 5 heap operations, which I have discussed earlier in the starting of this video. And only the find maximum. See, we are talking about max heap, and we are seeing find maximum. If we think, is this a max heap? Yes, because parent is greater than children. And if you say to, and if you ask to find the max element, find max, simply it is just the first position. You don't have any need to go to next level, next level, next level. So this is order of 1. So simply you can remember, and I will discuss in one by one simply, but for this time you can remember all the heap operations will take time complexity order of log n, and space complexity also order of log n. Only find maximum in case of max heap will take order of 1, because maximum element will be at the top. And if we talk about minimum heap, then find minimum will take also order of 1, because minimum element will be at the top of the heap simply. Now next operation we will say is delete max.